Yeah, on mine. Okay. Okay. Welcome to EE123 lecture 31. Woo! Okay, so a few things. We're going to do APRS stuff next thing, and then we're going to receive I recorded signals from the ISS. And in my other ham radio seminar, we made these measure tape antennas. Okay? You go like this. This is a VHF Yagi antenna. Very nice gain, about 7 dBi. Okay, so compared to a dipole. And it's tuned for the 2-meter frequency. So that's exactly the frequency that the ISS is transmitting down to Earth. And with this Yagi antenna, you're able to pick up really nicely the signal. This one is tuned. It took an hour and 30 minutes to make. If anybody wants to make that at home to receive signals from ISS, you're more than welcome. I can show you the designs. Really simple, just PVC pipes. This is measured tape. Clamps for, how do you call this thing that you water with? Water hose pipe. Yeah, water hose pipes. It's a coax, and then here's what's called a hairpin match that matches it to 50 ohms on the frequency. Really easy to make, super easy. Really recommend. If you want to do project-based, again, some of you wanted to do a radar-based project with the SDRs. That's one easy way to direct one antenna that way and another antenna that way. Making such a thing would be really easy. Okay, so this is design. This is design I took off the web, but it's basically the idea there is if you do a fox hunt, basically there's a hidden transmitter, and you want to run through the woods and look at it. It hits the woods, no problem. Antenna still works, right? As opposed to running with a expensive Yagi, like $100 and something Yagi that you bought is super optimized, and then within minutes it's gone. Okay. And the cool thing is wraps around like this. You can put it on your backpack, with some tape. Yeah, it's great. That's beautiful. I thought it was beautiful. So there's 2 designs like this in the ham shack. Anybody that needs access, if wants to test them, but also make them yourself, let me know. I'll post some the instructions. Yes, project. Okay. We're going to put the project more details on the website, but the idea here is that you need to select the project by next Friday. You need to submit 2 paragraphs, kind of project proposal. Really, what it needs to say is this is our project team. We're going to do that and that using that approach, 1 paragraph, and then here's how we're going to split the work. Okay? That's pretty much very simple, not something sophisticated. Okay? Especially if you're going to do the default project, which I'm going to explain what it is. By default, I don't mean boring, by the way. Default is really cool, too. So, I'm just saying that you could also do a default. Anyway. It's not default, the preferred project. Let's call it the preferred project. Okay. Project deliverable would be software that you're going to write, the demo, and a few slides poster. And we're going to have a time where we're going to, during, was that finals week or that week? Our week that we're going to spend a few hours on doing these. So you'll, after that you're done. You're done. You can do finals. You can do it. It's done. Okay. So you can focus on your other classes after this. Don't be overwhelmed. This is not. It's not too. It's going to be good. All right. A few slides or a poster describing what you're doing. The preferred project is going to be about image communication. So I've been teaching this class now for the fourth time. And the last 3 times we did image communication. I like it. I like images. This is what I do for a living, I like images. I like staring at images. Images are great. The cool thing about image communication is that you you have different type, but you can feel those images different ways, right? You see the images, but you also hear the images because you're going to transmit them. There's all these senses. And so it's really, I think, powerful way of doing this because you kind of see the signal processing happening. Okay, you see the signals, you kind of get more intuition of what is actually you're doing. Okay, but as opposed to the other last 2 years where it was a very specific project implementing a short scan TV, slow scan TV protocol, I've been working on your project for like last night, so forgive me. I'm trying to get you the GUI to do the nice. It's going to be great. I'm excited, but I haven't yet worked it out. So, like it's that close, and I'll post it. Okay, so as opposed to last years where we did slow scan TV protocol, which is an analog TV. You take like NTSC, whatever analog TV that people have used many years transmitting videos, and you want to fit the 6 megahertz bandwidth into 2500 bandwidth, 2500 hertz. So 6 megahertz squeezes into 25 hertz. What you do is you basically stretch it in time. So as opposed to having 24 frames a second, you're getting 1 frame a minute. Still get an image at the end. All right, so that was the idea there. So it's all analog. And I think now, analog's kind of, it's actually really cool. But at the same time, you can get really good image quality if you don't do analog, if you do digital. So I'm going to remove that constraint. It's not going to be, actually, you are not allowed to do Martin M1 protocol slow scan TV. Anything else is fine, but not the previous 2 year. Martin M1 is a particular protocol for SSTV. NTSC is protocol for analog TV in the United States before it was canceled. Then, so you're not allowed to do this, but accept. But we're going to make it into a challenge. You're going to have a minute to transmit. And during that minute, we'll give you an image which is like really high quality. So you'll have to transfer that image to another side, and you've got like 1 minute. 1 minute is like a number that I picked right now, but sounds like a good one. I might change it after I run my own simple default implementation just to give you kind of a baseline to start with. But let's say it's 1 minute. And you'll have to do something to that image to fit within this 1 minute. So you'll have to either compress it, you have to downsample it, both probably. You have to come up, use some way to transfer that image. What? Yeah, this is not material. Right? No, it doesn't count. Yeah, it's not reusable slides. It doesn't count. All right. Transfer that image to the other side, and it's going to have a loss of quality. And what you're going to want to have is to have the best quality image. And it's going to be measured by a measure called peak SNR, which is kind of a normalized mean square error, how much error there is. But it's also going to measure by a visual score. Right now, I'm thinking about staff scoring it. But maybe that's not enough law of large numbers. Maybe we'll incorporate you, but we'll see how that's going to work. Okay. So evaluation based on this, but you have like the best you could do in 1 minute. Okay. So you can send like 1 pixel, which is the average, right, of the image. Right. That's the worst, I guess you could do. I guess sending nothing would be the worst, but let's say just the average of the image would be like a result. Right, it's poor quality, but something, right? So you could get away with. Yeah. Now you can think about 4 pixels, 8 pixels. We'll see. So you can use any method you write yourself. That means that you cannot use libraries for signal compression. You cannot use, What? That's a good question. I would say that it should be general, rather than this particular. We'll give you an image to test on, and then we'll give you a different image to run the demo on. Yeah, no, for sure. No, of course you can use NumPy. What I'm saying is that you can't use JPEG compression. You can use DCT that somebody wrote, but you cannot use JPEG as a compression mechanism. Okay. Whether you could use error correcting code that somebody else maybe wrote, I'll think about that. Yeah.
So the 1 minute set, run the code, compress it, and...
No, just transfer for 1 minute. We'll think about whether, we're going to put in the specs whether there's going to be either a penalty for computation, but maybe this is going to be a small one that's going to evaluate. Like, we're not going to do like a Weissman score or something. But, yeah. Anyone else? That's a reference for the Silicon Valley HBO show. Anyway, those of you not watching, don't worry about it. Okay, so what you could do is, either compress or downsample, filter, I don't know, whatever you want to do to optimize the signal that you're going to be sending. You can filter it. You can do also post-processing to improve the quality afterwards. You can, affect the modulation. Either you do digital or analog. You can use the modem that you were going to build in or improve upon the modem that you're going to be building in Lab 6. Okay? So there's a lot of infrastructure you could already use to do this. Evaluation is going to be based on comparison to a particular a baseline implementation, which I'm going to implement with packet APRS. So I'm going to send like packets and construct an image with 1 minute, and that will be kind of the baseline. Any improvement upon that, we'll get starting at scores. Okay, because that would be the simplest case, like taking Lab 6, sending bits, and it's done. Okay. It's going to be also, of course, the scope. If you go and like implement like a new method for image compression that breaks everything that's on the market, yeah, you definitely get more credit for that. All right, like a publishable material, for example. Yeah, sure. And so on and so forth. But scope will be also creativity and, of course, the presentation. You're going to also be evaluated by this. Winner, winner, the one that gets the best, score, will get a prize. You get to keep the radios. Okay. So, and I'll have to talk to Win, but I think also the interface. Then you basically can reproduce your project at your leisure and show it to your family and friends. Yeah. Yeah, that's the motivation for, it's not a default, it's the preferred project. So that's why it's preferred. And you get a prize. But only if you win. Right? We'll see. I mean, if there's like a, if there's a tie, then, tie would win, so on and so forth. Okay, so now, I would not be the one that prevents creativity. And if somebody wants something to do something else, I have no problem with this as long as it goes along with the class. And I can give you a couple of suggestions that goes along with the class, but you could also come up with your own ideas. Last time there were some really creative stuff that people have done, and it was very impressive. So I would never want to stop you from doing this. It really depends on your time, your interests, and your level of, confidence in, whatever you want to do. You will need, though, to really present what you, for those that want to do a non-preferred project, then you would have to kind of convince me that it's a good idea. Okay? Because the preferred project, of course, I'm already convinced. So one example is phased array passive radar. What you could do is you can connect two of these SDRs clock and then make them synchronized. Remove one of the, here's an example that I picked from this website. You remove the crystal oscillator and you basically connect them together. So now the clock is synced. The USB sampling is not synced. You have to do that in software. But now you've got a coherent system with two receiver systems that are coherent. And now you can, for example, use one of these antennas with two systems, one directed at, let's say, an FM transmitter, like a radio, and then point that way so it's not that sensitive to that direction. And you can use that signal to detect Doppler as well as returns from targets, mostly airplanes. But you could also see sometimes meteors coming down to Earth using this. And this is an example of, what you would kind of get. This is, I guess, Doppler shift, and this is range, and this is about 600 kilometers. Okay, and then you can see that there's a lot of, there's some targets playing, and then let me just show you the video. That wasn't the video. You see the target changing Doppler? This is Doppler direction. This is range. It's pretty cool, huh? You can do that with two receivers. You can actually do it even with a single receiver. When you've got some sources, you can also do some correlation analysis. You can definitely see Doppler in, I see Doppler all the time happening at VHF frequencies. When you have a very narrow band transmitter, and then you just monitor that for a long time, you'll see these stripes coming through, and this is basically Doppler shift reflection out of airplanes. APRS packets, you'll see sometimes they'll kind of double because of Doppler shift. Yeah, so you see this? Pretty cool, huh? All right, so this is an example of I wouldn't say the most complicated, but quite challenging project. Another one that actually from last year, Gabe Buckmaster did a really nice project where he phased arrayed to basically connect them to two antennas, dipoles, and then in the receive you phase them such that you can electronically steer the antenna. So if you have an array of antennas with two antennas, arrays too, then you can have theoretically this type of a sensitivity pattern. You can basically eliminate your sensitivity to one direction by canceling the signal coming out from that direction. And focus it mostly on this direction. So if I have two antennas like this, I can really pick a signal from you from this direction, but I can cancel things that are coming from the side.
Good morning.
Yes, shut up. Okay, so then this would be, that was the theoretical, and this was kind of the practical one when he used car keys to go around and measure this. I think that's pretty impressive. So I recommend also doing this. This is really, with that you can also probably do range Doppler, direction Doppler. And if somebody wants to do this, you can actually do directional finding with at least 3 SDRs. 2 is not enough. Yeah.
So can that be done with transmission instead of receiving?
Yes, but you need 2 transmitters that are digitally you can actually control their phase. You can do that. Well, you could do it like with cables that different length, but then you cannot electronically steer them. If you want to actually steer them, you need to control the phase of the 2 transmitters, and your Wi-Fi does that all the time. You have 3 antennas or 2 antennas on a Wi-Fi router. They phase them such that you get directionality, so they can cancel interferences. The radios? No, your radios are not coherent. These are, that would be like 2 software-defined radios that have the ability to transmit. You'll be able to do this if you have 2 transmit chains. And there are some software-defined radios that would do that. You're going to see actually a lecture. Your last lecture before the midterm is going to be from Balint Siever, who's the guy that did this video on USRP. One of the first videos that I linked from the labs, there was this video of this guy showing what you could do with a software-defined radio. Yeah, he's going to come and talk to us. Okay, so this is another option. One option which I wouldn't say preferred, but it's I think it's a good idea because I like weak signal communication. So one thing you could do is try to implement a weak signal communication with on-off keying with your radios. With your radios, you can on-off key them using the the USB, and then you can receive at some other remote place with SDR, and try to communicate some digital information over a long range with really low signal-to-noise ratio. And that's inspired by JT65. It's a protocol for weak signal communication. But you'll see a link for this website. I'll post the slides online. But the idea here is that you can create a code. For example, this is a code of just on and off keying that has a narrow autocorrelation. Much like the chirp, remember was this pulse compression with the chirp? When we did this radar, you can think of it now as somebody's transmitting a code over a long time. And then somebody at another receive looking for this code by looking at correlations. And then once you actually have a detection, you'll get a large peak. Okay? And you can use different codes for different bits. You can use the polarity of the code to get plus or minus, and you can play all sorts of tricks to send information over several minutes. But you'll be able to pick it up maybe 100 kilometers from here, even with this, VHF radios. Okay, so this is another option that could be interesting. Any questions? But again, I'm open for other things if you really want to. These are things that I think can be implemented with I would say that the phased array and radar, a week is, you really need to know what you're doing. Or at least, you need to be feeling really good about it. Okay? This one, I definitely can think you can do in a week. Of course, the image communication, not a problem. Yep. I think what we said we did, the last day of like Friday, I think either Friday or maybe Thursday. We'll see maybe we'll do 2 sessions just because to minimize the amount of time we have to go through this, And I'll post your slides online. Yeah? So make them good. It's going to be there forever. Okay. Moving on. Linear phase. We talked about linear phase last time. We started actually talking about linear phase. Here's the difference between a linear phase. So what the advantage of a linear phase is that if you look at the group delay is constant for all frequencies. That means that all frequencies are delayed by the same amount. That's when you have a linear phase. There are certain conditions for a linear phase system to occur. This is, by the way, a minimum phase system. Remember what minimum phase has to have. All the zeros and poles have to be inside the unit circle. And in the minimum phase, you've got the minimum possible delay, a group delay for all frequencies. And that's why the impulse response looks like this. When you convolve with that kind of a impulse response, the delay is going to be approximately about up to 1 sample, right? Something like this. It's going to be how wide is the main lobe is going to be. That's kind of your delay. With the linear phase, the delay is half of your filter length. Okay? Linear phase filter have to be symmetric, and so it's going to be half your filter length. It's always centered at the peak is always in the center. And there's an interesting pole zero. When we're talking about FIR filter, there's no poles. All the poles have to be inside, at the center of the complex plane. But your zeros have to be in a very specific organization, such that any nonlinear phase that accrue by each one of those zeros, right? When you put just a single zero, it has a nonlinear phase response. It's based on the angle, right? The angles that we talked about when we talked about the analysis of what will be the group delay coming from a single zero. So there has to be a certain configuration such that this nonlinear component cancels. And it cancels when the other zero is exactly at 1 over conjugate position. And we're going to see that today. Going from minimum phase, for example, to linear phase gives you a certain adds cost for the fact that you want to have this uniform group delay across all frequencies. And so if you are going to choose a linear phase filter and you're only interested with the magnitude, that's going to cost you with either attenuation or passband, stopband ripple, or transition width. There's going to be a trade-off there that it's going to cost you by the fact that you want to have a linear phase. We also talked about the generalized linear phase, where it's not really the linear phase that we're looking for, is we want basically a constant group delay. And so if we can decompose a frequency response into this form, where you've got some real frequency response, this is a real frequency response that allows for signal changes. If the phase have a form of an affine function, so it's linear plus constant, then that is a generalized linear phase response. That would have a constant group delay across all frequencies, okay, this particular form. But in order to do this, you have to maintain a certain symmetry that would lead to this form of a frequency response. Your signal have to have a certain symmetry, otherwise the frequency response cannot be expressed by a real frequency response multiplied by some affine, basically an affine phase. Okay? Does it make sense? It has to be a certain symmetry, or otherwise it doesn't satisfy us. And so there are certain type of symmetries that need to happen such that we get this response. And we call them type 1 symmetry, type 2 symmetry, type 3 symmetry, and type 4 symmetry. Okay. Type 1 is when M is even. That means that you have odd number of taps of your filter. Okay? Odd number of samples. The order is called M, but the number of taps that you have, the number of coefficient is always M plus 1. Okay, remember that. So type 1 is M is even, and type 2 is when M is odd. And the symmetry that we're going to look for is an even symmetry. Okay? Even symmetry means that this will be exactly equal to this one will be exactly equal to this, and the middle one, whatever. Okay? This is type 1. Type 2 is where the symmetry, the mirror symmetry, is not around a sample, because now this is M odd, which means we have even number of samples. It's around the middle between these two samples, where this one is the same as this one, and this one is the same as this one. Okay? It's two different type of symmetries. Okay, one around the middle sample, and here is about, because there's no middle sample, is about the half, between the sample. Okay? That is the symmetry. In that case, A eta j omega, the zero phase, I call it, okay, because we are going to remove the generalized linear phase out of it. The zero phase response is going to have this particular form. Okay? And in this case, the zero phase frequency response is going to have this form. And as it turns out, for this case, the frequency, the value of the frequency response at pi is always going to be 0. Okay? It's always going to be 0. This case is not going to be necessarily 0. But this type of symmetry has to be 0. Why? 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 right. It has to have 0 at, right. It's 0 at the pi of 0 pole diagram. Yep. Yeah, what's the fastest frequency? What is pi frequency? Like, how do I calculate, the frequency response at pi? I have to multiply by something and then add, right? That's how I compute, right? What is e to the minus j pi n? -1 plus 1, -1 plus 1, right? If you multiply this by -1 plus 1, -1 plus 1, because of the symmetry, whatever you have here positive, you'll have here negative. And so it has to sum to 0. Where here, that is not the case. Okay? It will not sum to 0, and in fact, the value over here would be the value of this. The other, two coefficient will cancel, but this will be left. Okay? Does this make sense? -1 plus, right? Okay, great. So if you want to have this particular symmetry, we're going to impose it. And when we impose it, it's going to have a very particular frequency response. Okay, the zero frequency response, the zero phase frequency response. Because we have the symmetry when n is negative and n is positive, when we compute the frequency response, we'll have e to the plus j and for a particular n, and we'll have e to the minus j for the same coefficient. And those are going to add to be a cosine. Right? So that symmetry creates a frequency response which is really just a sum of cosines. Okay? The other one, you're going to look in the text and it will show you. But let me argue that you've seen this before. We're going back into the future, not back to the future, but back into the past. We're going to do a flashback. And remember the filter design problem that I gave you, and I told you, you want to design a linear phase filter using optimization method. And I said that the result is generally non-symmetric, but if we want to impose real and symmetric on the impulse response, then we'll get a linear phase, remember? And then I told you, we're going to talk about it later. Remember? This is now. Right? The later is now. And so you should have the symmetry. And then what we said is that h e to j omega is real symmetric. And because you have m is even, you have m plus 1 taps, then h of n needs to be real and symmetric around the midpoint. And in that case, if you compute the frequency response, then you've got, and I just reorder this from 0 all the way to, n, capital N, then you sum it's h tilde of 0 plus h1 e to minus, and then h minus 1 to e plus, and so on and so forth. And that leads to a cosine. That's exactly what you've seen before. Okay, that's exactly what I've shown you right now. Okay? So in that case, the only difference is that what I'm showing you right now is a filter which is shifted by m over 2. Okay? So this one is just causal. The other one was just not causal. That's the only difference. And the non-causality part just adds, just m over 2 minus k over here and this m over 2 here. That's pretty much it. Right? But it has the symmetry, again, around this midpoint. Okay? When you're going to design a filter, I would say, how about we just put the 0 over here? Just makes it easy to think. And then that's pretty much trivial. The problem is, though, is this symmetry, and this is the reason that I didn't tell you how to design filters that have m odd, because it's not trivial to center it around the middle, because there is no middle. And then you always have to design something which has a small linear phase component, because it's always going to be shifted a little bit. Okay, I cannot put the 0 in the middle here because there's just no sample. So this particular frequency response here is actually going to have a cosine, but the cosine is going to be shifted by 1/2, which is the half a sample that we're kind of missing here. Okay. If you think about it, it's kind of like half a sample. Okay. So this is the shape of the frequency response in this case. Okay, so these are type 1 and type 2. Any question? All it really tells you is, like, you want to design a low-pass filter with M odd, then it should have this frequency response. I can put that into the optimization matrices now. That will result in this, and I'll be good. Okay? That's basically what it means. The other thing that it means is, what if I want to design a high-pass filter with M odd, that's linear phase? Can I use the symmetry? No, but can I use the symmetry where I have this similar? This equals to this equals to this. No, I can't. Because it's always going to have a 0 here. There's no way I can generate a high pass with this type of a symmetry. Okay? Can I generate a high pass with this symmetry? Absolutely. Absolutely. Okay? So type 1 is good for high pass, low pass, band pass, whatever. Type 2 is only good for low pass, band pass. There's type 3. And type 4, they're the case where my symmetry is not even. My symmetry is actually odd. Okay? Type 3 and type 4 are odd symmetry. And odd symmetry means that, again, type 3 is around the middle, where M is even. And type 4 is around between the two samples, because this is M odd. Okay? In this case, if I have this type of a symmetry where this equals to minus this, then I can write my frequency response as a function of sinusoids. Okay? With a J here. Because this will result in a pure imaginary frequency response. Since it's a pure imaginary frequency response, then it has only generalized linear phase. It just has an offset of a J. Right? But it's still a linear phase. Generalized linear phase. Okay? And I can have another symmetry where this is odd, and then I need to generate the symmetry, and then I'm going to have kind of half a shift. A shift of half in my sign in the same way. Okay? One thing about this type of symmetry, it always have a 0 at 0 and at pi. Why is that? If you sum this, you get A, and that's DC. You always get a 0 if you sum this. Right? What if you modulate plus minus 1? Right? Negative, positive, negative. You sum that, you get a 0. Okay? So it always has zeros both in here and here. So this can only be a bandpass implementation on this type of a symmetry. Okay? What about type 4? Type 4 actually only has a 0 on DC. It doesn't have 0 at pi. Okay? When you sum this, it equals 0, but if you then multiply this by 1 and this by minus 1, then they actually have a value. Okay? So this can only be a high pass. Cannot be a low pass. In fact, this is, if you modulate this filter, you would get a type 2 symmetry. Okay, if I modulate this, I get a type 2 symmetry. Okay, so if I design, for example, a type 2 low pass, I can transform it to a type 4 high pass. Okay? There's no type 2 high pass, but when I modulate type 2, it becomes a type 4 because of that symmetry. Does this make sense? Okay, in order to generate, so the whole idea, here's the global thing. The whole idea is that I want to generate something that has a generalized linear phase form. I have to maintain a certain symmetry. If I have to maintain a certain symmetry, there needs to be some relationship between my samples. It should be either, if for any m that it's even, I can have either a even symmetry or an odd symmetry. That's going to put constraints on the possible frequency response that comes out of it. If I have m equal m that's odd, then I can also do an odd and even symmetry. And those will result in a certain frequency response. Okay? So now, if I want to design a filter, and I really want to null DC, I would not probably use type 1. I would either use type 3, 4, or that's it. Okay? Because I really want to null DC. If I don't care about nulling DC, I have more flexibility. If I really want to null DC, that's the only one that I could use. What if I want to null the Nyquist frequency? Then I can use really just type 2 and 3. Okay? I can get in all the other ones, if I increase the order, I can get a really low number, but I can really not null. Okay? If I just increase the number, it's going to decrease, but it's never going to be 0. So that's what's really this about. Certain symmetry that now, if I want to optimize for a coefficient, I'm going to impose a certain symmetry on those coefficients and then solve an optimization. Okay? And we did that for type 1. Okay? Because type 1 can do anything. But if you want a different type of symmetry that might give you some advantages in some frequencies, then you could use type 2, 3, 4, depending on your application. Does this make more sense? This is the global picture. And then for the details, each one of them will have basically a sum of some basis functions, which of course are going to be real, because it's going to have a real frequency response, right, with a general linear phase. So just the A part. So the A part, of course, I need to multiply by the general linear phase if I want to really implement this. Either going to be a sum of sine or cosine. If it's an odd symmetry, it's a sine. If it's an even symmetry, it's going to be a cosine. If m is odd, I'm going to have a shift by half a sample, like I have in this case. And if m is even, then I don't have that, because I need to have this half simple shift. That's pretty much it. I hope that makes it a little bit more clear. So now let's look at the zeros of these GLP systems. And we'll look at type 1 and type 2. Type 1 and type 2 have this form of a symmetry. H of n equals h of n minus m. Okay, that's the even symmetry. So if I want to look at the zero pole diagram for this, or the, yes. No, I think you're right. Let's see. Yeah, I think you're actually right. Is he right, Frank? I think he's right. Yes, because that will be negative, and that was basically not. Yeah, you're absolutely correct. Touché. I'm actually happy that you guys are paying attention. And I'm going to add you. Now you're at $2. Okay. All right. So now we're going to use this symmetry in order to basically put it in, right? Yeah, actually, this is what I did, in fact. Here, m minus n. Anyway. Yeah. Okay, so h of z equals to this, but that is also equals to the sum of 0 from m, the same thing, right? And if I have that, I can basically take z to the power of m out, okay, and write that as h of m minus n, z to m minus n, because I took z to the power 1 of m out, okay? This is just, sugar syntax. Okay? Now, I can call this, of course, k. I'll call this k. So really, I just sum, if you actually look at what I'm summing over, it's really the same as like summing k from 0 to m, just in a different order. And so what I get is that this frequency response look like z minus m, this frequency response. Which means that h of z also equals z minus m of the original one, h of z minus 1. Okay, this is the constraint that you have to have. So if you have a 0 at a particular position, you're going to have also a 0 at 1 over. Okay? That's pretty much what it means. If I have a 0 at one position, I'm going to have a 0 at another position. Okay? So, if I look at type 1 and type 2, type of symmetry, then whenever I have a 0 over here, 1 over actually would correspond to this one. But since this is a real signal, it doesn't really matter because I always have a conjugate here because it's a real impulse response. Then I always have a conjugate here. So this, so we always have these pairs. This one, and then this one doesn't have to have a pair. Okay? Because it doesn't generate a nonlinear phase. So any type 1, type 2 type of a frequency response will look like this, where you've got zeros at, in fact, for every 0 there's 1 over conjugate position. But because this is real, then whatever we derived was for real signal, so we came up to this, but it's true the other way too. Then they have to come in pairs. Okay. For type 2, because now our number of zeros is odd. Okay, because m is also the number of zeros. The number of zeros is odd, and in that case, one of the zeros has to be there on the unit circle. In this case, for that type of symmetry, it has to be here. Okay. So whenever you see filters that look like this, and you see one at that place, you know immediately if it's a type 1 or a type 2. Okay. So for general linear phase, basically if A equals R e to the j omega is a 0, then also 1 over A conjugate is also a 0. Okay. And if it's a real, then 1 over A is also a 0. Okay, if it's a real impulse response. Let's go quickly through type. I think we went over this. Why type 2 has 0 at pi? We talked about that already, so I don't need to show you that again. But similar, you can show that for type 3 or 4, you have all these constraints about, again, why it's a low pass, why it's a high pass, and I already shown you that too. So, finally, if we actually look at any linear phase system, we can decompose this linear phase system, okay, linear phase FIR system. We can always decompose it into a minimum phase, a maximum phase, and zeros on the unit circle. Always. Because what's a minimum phase? Is zeros inside the unit circle. Because it's a linear phase, we'll have to have zeros in the 1 over conjugate position, which is really taking those and making them into a maximum phase. Right? And then adding them together. And then, of course, zeros on the unit circles, which we don't have to touch. They don't affect anything. Okay? So one way to create a linear phase filter is to take a minimum phase filter and do a autocorrelation with itself. Autocorrelation with itself really, it's basically flips the, it's convolving it with a with its reversed. Reverses the maximum phase. The linear phase is the minimum phase is minimum phase, and taking minimum phase and basically autocorrelating with the maximum phase will result in this, in zeros outside, zeros inside, which cancels the nonlinear phase component and only leaves the delay. Okay? So in your homework, you're going to have a situation where, well, I need to have a minimum linear phase. What does it mean on my zeros? Okay? Now I want to create a delay which is lower than the the one thing that's important to emphasize is because linear phase systems have the symmetry. What is the group delay that they're going to have? It's going to be constant, but it's going to also be equal to m over 2. Always. Because it's symmetric. It's around 0, right? So it's always going to be, the main lobe of those filters is going to be around that. So for a low-pass filter, the delay is going to be around the middle of the filter, basically. So if you have a 500 length filter, you're going to have a delay, a constant delay of 250.